Okay. Good morning. Here we go. So I posted, because I'm not sure how fast we're going to be able to get through the functions. The functions part, because we spent so much time on the fundamentals, really the functions section, we're just going to kind of roll over it again and just kind of roll through things and just look at it from the function perspective. And so it should be pretty good. But I posted both the functions part 1 and part 2 just in case, and then I'll readjust them at the end of the week to kind of see where we're at. But for now, we're just going to look at functions part 1. And I'll bring this in here. What am I doing? I want to send it to Notability. I'm so used to uploading to my desktop. Second nature now. All right, where did you guys go? There you are. Unsupported file type. No. Create new note. Yeah. And I want it in here. Done. Okay. Sorry about that. Oh yeah, the test 1 solutions looming. I did not mark your tests yet. I managed to get sick right before the weekend, or on Friday. I was just completely down for the count. And then I've just been sick all weekend, so didn't happen. My apologies. But it's on the hit list today. All right, so don't you worry. It'll happen. Okay, so today we're going to start functions, but what did I want to say? Oh yeah, the final exam schedule is posted. I know Allison sent out an email to you guys, so you guys know, but let's just make a note of it here. So the final exam for us is on Wednesday, December 16th from 1 to 4. Okay. So pretty exciting to know when our final exams are, so we can plan around it, right? Going home, etc. If you're not home already, going away. No one's going away. What a bummer, right? So that's our final exam date. It'll likely, unless I find a different way of testing you guys, it'll likely follow the same pattern as test 1, where I post a PDF and then you work through it and then you upload your work to Gradescope, which I haven't had a chance to look at properly, but I did see that everyone managed to get a submission in, so I'm happy about that. And so it should be pretty good. Okay, so just looking through my list of things, but I don't see anything for you guys, so okay. So today we're going to start functions. Functions part 1. First thing we're going to talk about is just what is a function. A function is just a kind of a, people like to call it a machine. So it takes some input and produces some output. And so just by definition, the definition of a function is this, right? And we'll kind of do I don't know, a rougher version of it just to make things make sense, right? So a function f Usually a function is denoted by f. Some other common function names are g and h, or kind of v for velocity, that type of thing. So there's some pretty standard function names, but you could call a function anything you want. So a function f, just generally, is a rule. So it's just some sort of machine or a rule that takes an input x and gives you exactly one output, f of x. So we use this notation, f of x, and that's called function notation. So here, a function takes an input x and produces one output, f of x. That's f of x. So this thing you're going to read as f of x. Okay. So whenever you see something attached to brackets, usually those brackets denote of x. And so here you could do something like, here you would read this as g of x. You could even do something weird like cat of x, doesn't matter. Right, so whenever you see that something's smushed together with brackets and then x inside those brackets or something inside those brackets, you're gonna read it as of whatever. So if you keep going in stats, we use something like e of x, stuff like that. And so whenever you see these things, these are just, this is all function notation. Function notation. Okay. Where whatever's inside the brackets, right, is the input x. Let me scroll up here. So the input x is whatever, or the input in general is just whatever's inside those brackets. And then it produces f of x or g of x, cat of x, e of x, whatever you want to call it, right? And so here, if we go back to the general f of x, we've got x is the input and f of x is the output. Okay. Another key thing to keep in mind for functions is that f of x you can use interchangeably with y, right? And so if you're thinking about your xy coordinate system, then if it's easier for you to think about f of x as if it's y, then that's totally fine, right? You give it some x and it produces some y value. So we can also think of f of x as y, right? So if we think about our kind of coordinate system here, here I've got my x's, here I've got my y's, right? If I give it some input value of this x, right? Let's say I've got a line like this, then at this value of x, that should be a straight line. Not very helpful when it's not, right? Ooh, let me try again. Oops. Gone forever. Let's just do something like that. How about that? Better. So at this point, right, I've got an input of x and an output of f of x or y, right? Whichever you prefer to call it. So here, y equals f of x is at that point. We'll talk about graphing as well today. We've already graphed using Desmos, and I encourage you to keep using Desmos. I'm going to use Desmos as a really big crutch, especially because, x, do you mean x subscript I, Tim? You can use xi, yeah. But just in general, I'm just going to use x. So what Tim is saying is that technically we should have an x subscript I, but in this case, it's pretty obvious. So I'm going to ditch it just for simplicity's sake. So the x subscript I just denotes that it's any I, or any ith element of x, but it's okay. A point on this grid, right, is going to be an ordered pair, just like we've seen before, right? So we know that these are ordered pairs, and so we have x, f of x, right? Whereas before we were talking about x, y, right, as our ordered pair, but now we're going to start to think about these as x and f of x. Input, output. Okay. So, let's go to our notes, because there's a pretty helpful little graphic here that we want to talk about, because it's really important that we kind of get what a function is. So a function, right, if we go, I can't show the whole talk, but a function, right, a function f is a rule that assigns to each element x. So each element of x can only get exactly one element of f of x, right? So it can only get one output. And so each x can only produce one output. So keeping that in mind, right, here, an x of 1 produces an output of 20. We don't know what the machine is that does that. It's just called f, right? 2 produces an output of 20. It's okay for them to have the same output, right? As long as each element of x, right, or each xi, as long as it only produces one output, then you have a function. Versus here, right, an input of 1 produces an output of 10, an input of 2 produces an output of 20 or 30, right? And so that's what makes it not a function, is because here we can only have one output. A function can only produce one output per input, right? So that's why this second function, or the second relationship, let's say, is not a function. Okay, so that's going to be important. Okay. So in terms of function notation, right, we're going to use these to evaluate functions. So we're going to use function notation from here on out. Sometimes it'll be easier to just write it as y, right? Y equals f of x. But as long as you, in your mind, just kind of use them interchangeably, then you're okay. So let's steal some of these here. In fact, I'm going to shorten this a little bit. So it doesn't take up so much room. There, do some of these. So we'll start nice and slow, and if we have, oh, what happened here? Oh, sorry. It's, I don't know, getting a random phone call, but okay. Hopefully everything is recording, sharing. Okay, looks good. So we'll start nice and slow. And if we have some function f of x is x squared minus 6, for example, then this notation, f of -3, tells me that I need to put in -3 in for x. And so whatever's inside the brackets, that's your input, and then you generate your output. So we'll go nice and slow here. We'll start with 19. Then let's do a little bit bigger one. A bit. F of x is x squared minus 6. Yeah. So if I want to find f of -3, wherever I see an x, I'm going to replace it with -3, making sure that it's one thing. That's going to be more important later on. But just make sure that you're replacing it with everything inside the bracket, so the whole input as one thing. So -3 squared minus 6. -3 squared is 9 minus 6, I said 3. I really think we've talked about it before, but in case we haven't, right? Whenever you square a number, you should get a positive value, right? Squaring any value, negative, positive, whatever, is going to give you a positive value. So if you try -3 squared on your calculator, if you're getting -9, I'm just going to show you here, it's because it's doing negative on the outside and then 3 squared, which is wrong. So you want to make sure that you put brackets around that -3 and then square outside the brackets, and then you should get a positive value of 9, right? So just make sure that you are getting positive values for when you're squaring. In fact, I'll make a note of it here. Make sure you always get a positive value after squaring. Or any even power. Squaring / even power. So if we've got f of -3, we've got f of 3, we can do f of 3 is going to take 3 squared minus 6. That looks the same to me. So I'm just going to end up at 3, right? 9 minus 6 is 3. F of 0, f of 0, 0 squared minus 6 is -6. F of 1/2, making sure that you have the 1/2 in brackets and then square it, and then -6. So 1/2 squared is 1/4, and then -6. If you just use your calculator, right, you've got these fancy calculators, it'll give you it in exact form. Otherwise, you would have to go ahead and find the common denominator before you can subtract these fractions, right? So this is 1/4 minus 6. And then if we technically wanted to do it, I would multiply by 4/4 to get that common denominator of 4. So times 4 over 4 puts me at 1 minus 24 over 4, which is negative 23 over 4, which is the answer that I get on my calculator, right? So here, oh, that was not very nice. Or use your calculator. To find this. Just as a note, we've talked about it before, right? But this is the exact form. So the exact form of a number is not the approximate form, right? If you want the approximate form, especially if you're working on this calculator specifically, there's two options that I know of. Instead of hitting equals, you could hit the second equals. So shift equals has that squiggly equal sign. Or if you want to shift between the two decimals and exact answers, you can hit the S to D button. And so the approximation would be negative 5.75. That's an exact answer, but here, this is the exact answer. And this is the approximate answer, right? As soon as you're involving decimals, even though this one ends, so it's kind of like a gray area, I would call it the approximate answer. Kind of a gray area when it ends, but okay, good. So for this one, right, we have been working so much with these fractions, so we should be really good at combining fractions like this, right? So it really shouldn't be that big of an issue. But if you find that it saves you time, then just going straight from, well, maybe here, 1 over 4 minus 6, to negative 23 over 4, that's totally fine, right? You can use your calculator to do that. Yeah. Let's do 22, a little bit harder. I'm going to copy it so I have it on this next page. Oops. Okay, so we've got h of x is x squared plus 4 over 5. And first thing I want to do is find h of 2. So wherever I see an x, I'm going to input 2 and see what I get. So I get 2 squared plus 4 over 5. 4 plus 4 over 5 puts me at 8 over 5. And I'm just going to leave it like that. We try to leave answers in exact form unless specified, right? Unless I tell you to 4 decimal places, to 2 decimal places, whatever, unless specified. Sometimes I'll get you to report things in decimal form, but then I'll tell you how many decimal places. So unless that's the case, I want it in exact form. So h of negative 2, wherever I see an x in here, I'm going to replace it with negative 2 in brackets. Right, so negative 2 squared plus 4 over 5. This is going to look the same as my other one, right? 4 plus 4 over 5 is 8 over 5. Okay, so we get the same answer. H of A, and this is going to come up later, right, where we need to just be able to replace it with some other variable. So H of A, again, wherever I see an X, I'm just going to replace it with A. So H of A is A squared plus 4 over 5. There's nothing more I can do about that, so then I'm done. H of negative X is negative X squared plus 4 over 5. Now, I would probably just leave it like this. If you wanted to write it as X squared plus 4 over 5, that's totally fine because you know that that negative would go away. But I would probably just leave it like this. Maybe I'm lazy. No, but it's nice to see that it's that negative X in there. If we go on to H of A minus 2, so now we're kind of getting jiggy with it. H of A minus 2, let me see here. I'll put it, because I want to have it on the same page. H of A minus 2, remember, so A minus 2 is one thing, and it's going to replace X. Wherever you see an X, you're going to replace it with A minus 2. So you're going to have A minus 2 squared plus 4 over 5. Because at a glance, I'm looking at this thing, and it looks like I might be able to get a negative 4 out of here, which would cancel with this 4. I'm going to keep going, and I'm going to expand this A minus 2 squared. A minus 2 squared is A minus 2 times A minus 2, right? And so you want to make sure that you expand it properly. But what we get, I'm going to move it over just a little bit, A minus 2 times A minus 2 plus 4 over 5. A times A is A squared. A times negative 2 is negative 2A. Negative 2 times A is negative 2A. And then negative 2 times negative 2 puts me at plus 4. So they didn't cancel, but it does look a little bit nicer here because I get A squared minus 4A plus 8 over 5. I would say you could definitely just leave it like this. This is fine. It depends on what you're doing, so what you need this thing for later, right? Sometimes it's easier to expand it out and just have this kind of expanded version, or if you want to call it a factored version, then that might be helpful too. So it kind of depends on where you're headed with this thing. For now, I just wanted to show you that this would expand to this. And then finally, if we do H of root X, so now wherever you see an X, you're going to replace it with the square root of X. So we've got H of root X is root X squared plus 4 over 5. Root X squared is just X, right? X plus 4 over 5. So we need to be really good at just being able to plug stuff into a function. But compared to some of the other stuff that we were doing, right, those rational expressions, for example, right, fractions and fractions and fractions, this stuff is not that bad, right? So we're just kind of involving functions more. Okay. For piecewise functions, we've already seen piecewise functions, right? In the absolute value of X, right? But piecewise functions, they just tell us, okay, well, it's going to be this function for this portion of X's, And then for the next portion of x's, it's going to be this function. So you could have a combination of functions that kind of meet at some point. And so depending on what your input is, it'll depend, the input will tell you what the function that you need to use is. So let's do, just to mix things up, or maybe let's do a hard one right away. How about that? 34. Ooh. No, it's okay. So what does this thing say? So a piecewise function, usually we just have f of x, and then we combine them with this big curly bracket to the left. And so it says, okay, well, the function is going to be 3x if x is less than but not equal to 0, right? So for anything that's less than 0, the function that you're looking at is 3x. If x is between 0 and 2 inclusive, right, then the function that you're looking at is x plus 1. Whereas if x is greater than 2 but not equal to 2, right, so notice how they trade off, right? So here's up to 0 but not including 0. Here's 0 including 0, up to 2 including 2, and here's everything past 2 but not including 2, right? You have x minus 2 squared. So depending on what your input is, right, where does your input fall in here, that's going to determine which function you're using, right? And then you can find your output. So if we do 34, f of -5, well, -5, so an x of -5 is when x is less than 0, right? So here, x is less than 0, so f of x must be 3x. F of -5 then is 3 times -5, which is -15. How about f of 0? F of 0 is right on the cusp where it kind of changes from one function to another. So now you need to make sure that you have where it's equal to 0, right? So if x is 0, then the function that you're looking for is x plus 1. So for f of 0, is x plus 1, which is 0 plus 1, right? And that's because x is equal to 0. Oops. So f of x is x plus 1. So piecewise functions are not, not that crazy. It just involves that extra element of figuring out where your x is in this range and then picking the appropriate function after that. So let's do these other ones. F of 1 if x is 1, x is between 0 and 2, so the function that we're looking at is still x plus 1. So f of 1 is x plus 1, which is 1 plus 1. But you didn't think we'd be doing 1 plus 1 today. But here we are. So f of 2, same deal, right? Same, it's on the cusp, right? But we have to figure out where the x is including 2. Here at x greater than 2, it's not including 2. So our function is still x plus 1. So I'll put it here, 2 plus 1, which is 3. And then finally, f of 5, well, 5 is greater than 2, and so now our function is x minus 2 squared. So we've got f of 5 x is greater than 2, so f of x is going to be, what was it? X minus 2 squared. F of x is x minus 2 squared, which is 5 minus 2 squared. 5 minus 2, so remember, BEDMAS, right? You have to do what's inside the brackets and then the exponents and then kind of bloom out like that. So that's going to be 3 squared, which again is 9. Frequent flyer today. 3 squared. Okay. So, I'm getting used to function notation mostly, but nothing really crazy going on today. So, the net change of a function is just the change from an input of A to B, right? But just like when we had to find the distance between 2 points, what we do is we find the second output first and then subtract the first output to get the net change. And so the net change here, just copy it in, is going to come into play a little bit later when we talk about the average rate of change. But for now, we're just going to talk about the net change. And so the net change in the value of a function f as the input changes from A to B, as long as A is less than B, or that's what it's assumed, right? Then the net change is from the output at B minus the output at A. If we think about a graph, here's my x, y grid, right? Here, if I'm at A and if I'm at B, right, that's what it means where A is less than B, right? A is less than B on this number line. And so the net change is going to be from, let's see here if I can, going to go like this. Then the net change this point here is f of A, and this point here is f of B, and I'll put some dots on there too. So the change in your y's, that's your net change. All right, your overall change. So what can happen in here is you could have a function that looks like, let's just do, you could have a function that looks like this, right? But the net change between A and B is only this much, right? F of A and F of B. So the net change is really just the overall change in the outputs. Okay? So let's see if we can do some of these. So we're going to find the net change between the given inputs, right? So let's do the last one. If we have 42, h of t is t squared plus 5 from t equals -3 to 6, right? T is our input, because that's what's our input in our function, right? And so, and also it's the variable in our function, so that's what makes it the input. So from t equals -3 to 6, the net change is f of b minus f of a, which is going to be, in this case, right? We generally talk about f and f of b minus f of a, but in this case, our function is called h, right? And our a is -3 and our b is 6. So what we have is h of 6 minus h of -3 is what we want. H of 6 minus h of -3, right? That's our net change. You would probably get there just by looking at this and saying, okay, well, I need to find the output at the second point and then the output at the first point and subtract the two. But this is what that would look like mathematically. So keeping in mind, right, that h of 6, that's a function, and then h of -3 is a second function, so you can evaluate these separately and then bring them together, right? So you'll want to make sure that you don't mix these two up. I'll move it over just a little bit. So what I like to do is I like to put kind of big square brackets around each of these functions, especially if things get kind of messy and they are about to in the next example, right? It's nice to just keep things blocked off. So what I do is I just do big square brackets. H of 6 is 6 squared plus 5, right? That's h of 6. Minus h of -3 is -3 squared plus 5. So you want to keep those separate, and you're going to deal with these brackets first. And so we have, and you'll want to definitely make sure that you're doing the right thing with your calculator. So 6 squared is 36 plus 5. It's going to be 41, but first I'll deal with this one. -3 squared is 9. 9 plus 5. So we get 41 minus 14. And just always confirm. So the net change from -3 to 6 is going to be 27. Okay. So when do things get tricky? Definitely get tricky when we involve the difference quotient. So the difference quotient, I would just give it to you, but the difference quotient is this whole thing. So the difference quotient we use a lot in calculus, and so I know one stream of you goes into calculus, or maybe you have the option of taking calculus. Can't remember right now. But if you do, then you'll definitely be working with the difference quotient. So it's good to get comfortable with the difference quotient. And we've sort of seen it before. The difference quotient is used in calculus, and it is f of a plus h minus f of a divided by h. One really nice thing is that if you've done things right, this divided by h should go away, right? So it should cancel out and you shouldn't be dividing by h anymore. So If we have to find f of a, then that's easy enough, right? And so if you have f of a, you can plug it into here. F of a plus h, we saw something similar just earlier, right? And so f of a plus h, you can evaluate it on its own and plug it in here, right? And then you can smush the two together and typically expand and simplify, and we'll do one. Let's do two together. So let's do 44 together first. Okay, so f of x is 3x squared plus 2. First thing I want to do is I want to find f of a, and then I'm told to find f of a plus h, and then I'm going to find this difference quotient. Even if it had just said, go find the difference quotient, I would still break it up into these little sections and then combine them into the big thing later. So here, f of a, well, f of a, I'm just replacing x with a, so that's going to be 3a squared plus 2. F of a plus h is going to be 3a plus h squared, remembering that that square is on the outside of the a plus h. So I can expand this. Keeping that 3 on the outside, I get a plus h times a plus h plus 2. And maybe move this over a little bit so that I have a little bit more room here. Expanding this, a times a times h times a is really the same as a times h, and then h squared. So I get 3 times a squared plus 2ah plus h squared, and then plus 2. I'm going to expand this 3 inside, right, to see if I can simplify anything. It doesn't really look like it, but it might just be nice to not have any brackets anymore. So 3a squared plus 6ah plus 3h squared plus 2. Making sure that you want to, that you can, sorry, that you expand the 3 onto each of the terms, right? You don't want to forget about an h squared, for example. There's nothing more I can do to simplify this thing, so I guess I'm done. So now what I'm going to do, the last thing I want to do is I want to find this difference quotient. So now I'm going to combine these things to find the difference quotient. So I want to find f of a plus h minus f of a divided by h. Again, I'm going to make use of these big square brackets. First around f of a plus h, which is the one I just found, 3a squared plus 6ah, oops, plus 3h squared plus 2, minus f of a. F of a we found was just 3a squared plus 2, making sure that you treat that as one thing. So you put big brackets around it. 3a squared plus 2, yep. All divided by h. Okay. So now the brackets around f of a plus h aren't actually doing anything, but they are doing something around f of a. So when I expand this out, I have to bring this negative onto both terms. If you don't, that's where things go wrong. And so that's when things won't cancel and you won't be able to cancel this h. So that's a very common mistake. So let's get rid of these brackets. 3a squared plus 6ah plus 3h squared plus 2 minus 3a squared. Oops, I almost did it myself. Minus 2 divided by h. So I get plus 2 minus 2. Those are going to go away. 3a squared minus 3a squared, that's going to go away. So all I'm left with here is 6ah plus 3h squared divided by h. Because I can pull out a common h here, I'll be able to cancel it with this h. So I'm going to rewrite this as 6ah plus 3h squared divided by h. If I pull out that common h times 6a plus 3h divided by h, because I'm multiplying this h by everything else inside the brackets, that's when I'm allowed to cancel this here. So now I can cancel these guys, and I'm left with 6a plus 3h, and then I'm done. So let's do one more. Which one are we gonna do? Let's do one with a fraction in it. Let's do 48. 2x over, let me just find it here. Okay, so I can copy it. So 48 says f of x equals 2x over x minus 1. So first thing I'm going to do is I'm going to find f of a. F of a is just 2a over a minus 1, so that's fair enough. Then I'm going to spend some time finding f of a plus h, and then I'm going to combine the two. So first things first, f of a is 2a over a minus 1. F of a plus h, well in this case, right, I've got two x's in here. I've got 2x over x minus 1. And so now, making sure that you treat a plus h as one thing, you plug it in for x. And so you get 2 times a plus h divided by, and make sure you put those brackets around a plus h, just in case there's a negative being brought in or something weird like that. A plus h and then minus 1. I can expand this a little bit, right? Not too much, but a little bit. So let's just go ahead and do that. So we get 2a plus 2h over a plus h minus 1. Okay, so now I've got, where was it here? I've got f of a, I found f of a plus h, so now I'm going to combine them and find the difference quotient. So f of a plus h minus f of a divided by h. Big brackets around each of these, f of a plus h, f of a, and then divide by h. Don't forget dividing by h. Sometimes it can get lost in the shuffle. But what I'm going to do is I'm going to take 2 rows for f of a plus h and f of a because it's going to be a fraction and I want to deal with those properly. So 2a plus 2h divided by a plus h minus 1. That's my f of a plus h. Minus my f of a is 2a over a minus 1. All divided by h. This looks nasty. So what I'm going to do is, well, I've got these, a fraction minus a fraction. I know I need a common denominator. There are fancier ways that you can do it, right? But what I do is I just use these two multiplied together as the common denominator. So that means that this numerator is going to be multiplied by a minus 1, And this 2a is going to be multiplied by a plus h minus 1. And then my common denominator is going to be these two multiplied together. So let's deal with that first. I get 2a plus 2h over a plus h minus 1 times, so this is being multiplied by a minus 1 over a minus 1. Just to get that, force that common denominator. 2a over a minus 1, and this is being multiplied by a plus h minus 1 over a plus h minus 1. And that's all over h, don't forget it. Whee! Make a nicer h. Okay, so now I've forced this to be my common denominator. So what I'm going to do is I'm immediately going to write these over a common denominator. Maybe I spoke too soon. I like to go nice and steady. I'm going to give myself a little bit more room because it's getting kind of crowded. But I get 2a plus 2h times a minus 1, right? Making sure that you treat this as one thing times another thing, right? So keep those brackets on there. And then minus, and this is all inside the minus, 2a times a plus h minus 1. Making sure that you bring this negative onto each of these terms. All over that common denominator of a minus 1 times a plus h minus 1. And that's all over h. We know how to deal with a fraction over a fraction, right? That's what we've been working on before. And so h is really just h over 1. So you've got a fraction over a fraction. So you'll be able to simplify this a little bit. But for now, I'm still going to keep that h in the denominator until I'm able to clean this up potentially a little bit. So this becomes 2a times a, which is 2a squared minus 2a plus 2ah minus 2h. Uh-oh, I'm going to need way more room. Whee! Minus, and I'm going to keep that minus outside until a little bit later. Once I've brought this 2a onto each of these terms, then I can focus on bringing in this negative properly, but I don't want to muck it up. So 2a squared plus 2ah minus 2a divided by, and what I'm going to do, I'm going to expand this and simplify it hopefully a little bit. A times a is a squared plus ah minus a minus a minus h plus 1. Okay. Let me just double check. A times a is a squared, ah, negative a, negative a, negative h. Yeah, good. All over h. Whee. So let's cancel some stuff, right? Or hopefully cancel some stuff. Once I'm able to bring this negative onto each of these terms, right? I can see that 2a squared minus 2a squared is going to go away, and the 2ah minus 2ah is going to go away. So there's quite a bit of simplification that's going to happen here, and this is what's so rewarding about these things, because they kind of balloon out of control, and then things cancel, and you slim down to almost nothing usually. So we have 2a squared minus 2a plus 2ah minus 2h minus 2a squared minus 2ah plus 2a divided by, and I'm going to simplify this denominator here, a squared, what else, plus ah minus 2a minus h plus 1. We'll start there. A squared plus ah minus 2a minus h plus 1 divided by h. Okay. So here we go. Let's see what we've got. We can cancel, just like we said earlier, right? 2a squared minus 2a squared, find 2ah minus 2ah, that goes away. Negative 2a plus 2a, so all of those are going to go away. So what I'm left with is 2a squared minus 2a squared. And I encourage you to cross them out as you go so you're not kind of leaving anything behind. Minus 2a plus 2a. So all I'm left with here is negative 2h up top. Okay. So what I get, this becomes negative 2h over a squared plus ah minus 2a minus h plus 1. Not really seeing anything that I could do to simplify this unless I wanted to. I could probably have kept it like this. I might go back to that, but often it's time, or it's nice to expand and then see what happens, and then, but just keep this up your back sleeve. As long as you haven't canceled anything, you can still use this as your factored version. So let's see what happens here. Treating this as a fraction over a fraction, right? You've got a huge fraction over h over 1, right? H over 1 is a fraction, which you can flip and multiply. And so I guess I'll write it out one more time. All over h over 1, which becomes negative 2h over a squared plus ah minus 2a minus h plus 1 times h over 1, flip, 1 over h. Now I'm able to cancel this h with this h because I'm multiplying, right? This h is multiplying all of these terms, so that's why I'm able to cancel these. And so I'm left with negative 2 over a squared plus 8h minus 2a minus h plus 1. As soon as you've canceled this h, right, this h that's been hiding in the denominator this whole time, that's when you're done. Usually you've simplified things as much as you can up until that point, and so as soon as you're able to cancel that one, you're done. Nice. So here it is, the difference quotient. It can make your brain hurt, but like I said, it's going to be really, really helpful if you just figure out what each of these components are individually, like we did here. So f of a plus h is this, f of a is just f of x with a's instead. And then compile them carefully with brackets and find the common denominator and just kind of work towards canceling this h eventually. And things will cancel out a lot. And then, all right, looks nasty, but it's okay. Because you're just working towards slimming this thing down. Good. So, we've talked about the domain already, right? In 1.4, in section 1.4, we talked about the domain. So I'm going to leave these for you guys to work through on your own. Some of these are harder than others. Just remember that for the domain, right, we cannot divide by 0 and we cannot take the square root of a negative number, right? And so oops. From section, I want to say 1.4, recall that the domain is all possible values of x. So the domain excludes illegal values of x. The domain excludes illegal values, I'll put it in kind of quotes, right? We can't divide by 0. You can try it on your calculator, but it won't let you because you can't. And we can't take the even root. Usually we talk about the square root. We can't take the even root of a negative number. Right? Typically we talk about the square root, the second root, but fourth root, sixth root, whatever, any even root behaves the same way, so we can't take the even root of a negative number. So these are the things that we have on our roster and things that we need to eliminate from the domain in order to have a true function. So I guess we can do one. We're asked to find the domain of the functions. And let's do 70. 70 says f of x, so the function is x squared over the square root of 6 minus x. What we need to make sure, right, is that all our inputs don't give us a division by 0, right? So if the square root of 6 minus x equals 0, we have to pull those values of x out of the domain, as well as any x's that give us the square root of a negative number, right? And so we need the root of 6 minus x to be greater than 0. I jumped the gun a little bit. We need to make sure that the root of x, 6 minus x, does not equal 0, and that 6 minus x has to be greater than or equal to 0. Right? Can't divide by 0, so here I'm dividing by 0, so I'm going to make sure that the root of 6 minus x does not equal 0, but also I can't take the square root of a negative number, and so I need to make sure that 6 minus x is greater than or equal to 0. I can take the square root of a negative number, but what we'll see is that's when the root of 6 minus x equals 0, so we're also going to pull that out. But so we've got the root of 6 minus x cannot be 0. Solving for x here, treating this inequality as if it's an equal sign, keeping track of those negatives, right? If we're multiplying or dividing by a negative, we have to switch the sign. Not an issue for not equal to, but it is an issue for here, greater than or equal to 0. So we get 6 minus x is not equal to 0 squared. 0 squared is just 0. So I usually just subtract or add x to both sides. even though I like to solve for x on the left-hand side, but what we get is 6 cannot be equal to x, right? Which makes sense. 6 minus 6 makes 0. The square root of 0 is 0. So therefore, x cannot equal 6. Okay. Now, we want to make sure that 6 minus x is greater than or equal to 0. So 6 minus x has to be greater than or equal to 0. 6 has to be greater than or equal to 0. Sorry, x. If I add x to both sides. If I'm just adding x to both sides, I don't have to switch the sign. And so x has to be less than or equal to 6. We want to read it that way. So therefore, x has to be less than or equal to 6, but the combination of these two, x can't be equal to 6, and x has to be less than or equal to 6, well, x has to be less than 6. So we combine these to say that x has to be less than 6 is the domain of f of x. Oh. Good. So we've seen domains before. It's kind of a refresher. We didn't see it in terms of a function like this. I think we just had the expression, but now we're talking about a function, and the function has some domain, so some reasonable values of inputs. Okay. I haven't seen any questions, so I guess I'll just keep going. The next section is talking about graphs, okay, graphs of functions. We've been using Desmos for graphs, and I really want you to keep using Desmos for graphs. But it's going to be useful to know the typical shapes of some of these common graphs. So what do you expect when you see an even power, for example? Well, you expect to see something like this. What if you have an odd power? Then you expect to see something like this, right? What does a linear function look like? Y equals mx plus b, or f of x equals mx plus b. Then we get this straight line that can have positive or negative slope, which are all things that we've already talked about, right? And so we haven't really talked about reciprocal functions, but it's good to know what they might look like. Even root functions, we haven't looked at what they look like, but just in general, these are the general shapes that they take. The absolute value function is this kind of v, and we're not really going to talk about the greatest integer function, but it's there in case you need it. Let's see here. So graphing functions by plotting points is not something that I, want you to do. I would say instead of making a table of values, so that's your x, y coordinates, you plug in some value of x, you figure out what the value of y is. I would encourage you to try these, right? But then double check your work with Desmos, right? And so here, dark. Making a mess here. There we go. 2.2 is graphs. It's not really 2.2 in your textbook, but it's just, I'm finding it easier to just use these notes that I've already made up because they're way cleaner than the textbook. Um, so for graphs, Desmos might show domains. I think it would. Let me see here. Let's try something like, oh, that's the calculator. I downloaded the Desmos calculator. I guess there's a Desmos calculator, which is that 3 root 27 or the third root of 27. Go to the Desmos graphing one. For the record, I don't know, I didn't really love the calculator, the Desmos calculator, but it's nice to have. So if I graph something like the square root of x, it does. So it does show the domain, right? Because what we know about the square root of x is that, well, I can't give it any negative values. So notice that there's no line for x is less than 0. So I can take the square root of 0, but I can't take the square root of a negative number. Now, you can't see me, but I'm kind of going into the negative direction on the x's, right? So here, there's nothing, and so it will show you the domain of these graphs. Nice. So for graphs, we can graph functions by evaluating the function at different values of x and finding the f of x ordered pairs and plotting them. And plotting them. I guess there's a but coming. So we can graph functions just by plugging in different values of x and seeing what these things look like. But if you do that, but always check your work using Desmos, right? So, but always check your graphs using Desmos. Sometimes if you're plotting points, it can be hard to figure out what the shape is, right? So it's useful to know what the shape of a typical graph is. So it is useful to know what shape to expect for some typical graphs. And that's where I'm going to bring in this table that you have. Okay. So of course, a linear function, we've talked about those already, and we'll talk more about linear functions. But power functions, in general, if you've got these even powers, you have something that goes like this, right? Which makes sense. If you take the square of a negative number, it still gives you a positive output, right? And it's going to be the same output as if you put in that positive number. In general, an even power looks like this. And odd powers look like different color. Look like this. Notice that as the power increases for even powers, the graph just kind of sits down on the x-axis more, right? So it just becomes more kind of on the x-axis. And then same thing with as you increase these odd powers, you've got x to the power of 3, just kind of lightly touches the x-axis, or like approaches the x-axis. Here it hangs around the x-axis a little bit longer, right? And then it shoots up. You can find similar kind of trends with even roots, right? So odd and even roots. So if you have the square root of x, then it doesn't include, so in the domain, you don't have any negative x's. Same thing with the fourth root of x, and that's what we were saying earlier, right? You can't take a negative root or a negative even root of x. And then same thing, you are allowed to take odd roots of negative numbers, and they give you negative negative outputs, and kind of see how they're kind of rotated, just been shifted. And I'm going to put off the reciprocal functions, the absolute value functions, and definitely the greatest integer functions for now. And just as long as we know what these three look like, then I'll be happy with that. Know what these three functions look like. In general. Okay. So, for the graphing, I'm going to leave it to you to kind of use Desmos, check your work, make your table of values, right? But all you're doing, just like when we were graphing lines, right? You just plug in some value of x, some easy value of x, and then you figure out what your output is, what your f of x is, and then you can plot those points and, but just confirm using Desmos. Yeah. So we're talking about functions, right? Functions, there are some expressions that are not functions. And so what we can do is we can use the vertical line test to determine if a graph represents a function. We use the vertical line test. The vertical line test to determine if a graph represents a function. So what it says is that, okay, if you've got some sort of graph or some sort of curve, it's going to be a function if and only if no vertical line, so remember vertical, horizon, horizontal, so no vertical line intersects the curve more than once, right? So if you've got your graph in Desmos, for example, if you're able to look at it and if every single possible vertical line that you could possibly draw, if it only intersects the graph once, then you have a function, right? If it intersects the graph more than once at any point, it's not a function. Okay, so let's see here, we can have a look at something like this. We've got 4 different functions to look at here. So by the vertical line test, okay, if I draw vertical lines all the way along here, it looks like I only intersect the graph once, right? Making this a function. So this is a function. Going to the next graph though, right? If I graph this, and we know that we could have graphs of ellipses and circles and all those things, but the key thing is it's not a function, right? And so, and if you think about the definition of a function where we started, well, each input of x, so x equals 0, can only yield one output, but in this case, it's giving you two outputs, right? And so here, if I draw this vertical line test, in fact, at any point, it crosses more than once, and so it's not a function. Okay. Moving on to this next one here, in 55, well, at x equals -1, what we get is we get this range of outputs, making this not a function, right? Because at every single point here on the y-axis, that's an output. So this, not a function. Here, this next one, if I'm moving my vertical line across here, so far so good, vertical lines, vertical lines. The only place that I might run into trouble is here, but at x equals -1, it is at this point, right? We've got a closed point here and an open point here, so that's where they're doing a trade-off. And so I've still just got one output at x equals -1, and then it continues and I'm able to draw my vertical line once more. So this is a function. Okay. So where did we talk about? It also wants us to talk about the domain and the range. We haven't talked about the range, but I think you've probably heard about it before. So the domain, remember, is all possible values of x. The range is all possible values of f of x, so all possible output values. All possible values of f of x. Remember, f of x is y, right? Or we can say all possible output values. Okay. So here, for 53, if we go back and look at the domain and the range, the domain, it's going to start here at -1, 2, 3, -3 to +2. So what we can say for 53, the domain is when x is, and it seems to be inclusive, right? Because we've got this closed dot, closed dot. So from -3 to +2. Okay. In interval notation, if we're including -3 up to 2, we use square brackets. Okay. For the range, now we're looking at all the possible values of f of x, which are the outputs. So our output seems to go from +2, and the lowest it seems to go is to -2. So usually we have to write from a smallest number to the largest number. So the range, f of x goes between, and it is inclusive of these points from -2 to +2, or in interval notation from -2 up to +2. Usually we give these answers in interval notation, but sometimes it's nice to kind of put them like this in inequalities. Just depends on what you like. For 54, there's still a domain, right? The domain here is from -1, 2, 3 to +3. And same thing with your outputs, go from -1 to +1. So I'm just going to use interval notation. Looks like it's inclusive of these things. So from -3 to +3, and the range is from -1 to +1. For the next one, 55, right? If I want to talk about the domain goes from -1 to +3, inclusive, right? And so the domain is from -1 to 3. And the range is from 1, 2, 3, -3 up to 1, 2, 3, +3. And just keep it on the same page here, for 56, I get a domain from -1, 2, 3 up to +2, right? It doesn't matter that we've got this skip here, we've just got a piecewise function, but because the function continues all the way through, all of these are in the domain. Now I can't remember what I said, -3, I think, to +2, let me just confirm. 1, 2, 3, yep, +2. For the range, okay, I've got outputs here at -2, and from, let's see here, 0, but not including 0, up to 1, 2, 3, right? So what I would say is I would say the range is, here's where things are going to get weird. I'm going to break these up. I'm going to say from -2, including 2, including -2. So from -2 to -2, now that's kind of weird, right? But that's just to indicate that, okay, here's the range, it's from -2, it's just -2, instead of just putting one value. Union, right? So or just kind of linking these two up, or from, and then not including 0 because it's an open dot at 0 to +3. Oops, but including 3. There. So, all right. We will talk more about the domain and range of functions, but it's just good to be able to look at a graph and see what it might be. I'll leave these exercises for you to work through. We've got bigger fish to fry. So we can use the graph of a function, right? Just like we were doing. So here's a little summary. The domain is all the possible x values, and the range is all the possible y values. So we can use Desmos to find the domain and range, just like Tim asked before. So using Desmos, you can generate the graph and you can look and see what your possible inputs and outputs are, domain and range. The main thing from this section is if we're solving equations, so if we have something like this equation equals another equation, where that's true is where they intersect, right? And that could be at more than one point. And so what we want to be able to do is we want to look at a graph using Desmos, right? So whenever you see this little calculator thing, definitely use Desmos. It's not meant for you to do by hand. So this little calculator shows up a lot in these sections, right? And so definitely use Desmos to solve these. But call it 2.3, getting information from graphs. We can solve equations and inequalities. I'll show you how here. Inequalities graphically using Desmos. So for example, if we go and we steal this little graphic here, if I have two functions, f of x and g of x, where they're equal to each other, that's going to be where they cross, right? So where there's an intersection, right, that's going to be the solution. So the values of x where the graphs of f and g intersect. Okay? If you're talking about an inequality, if this is the graph of f and this is the graph of g, if you want to show where f of x is less than g, right, all the values where the outputs of f are less than or just below the outputs of g, that's where the solution is. So the solution would be from this intersection to this intersection. So let's use Desmos to try some of these together. Copy. So we'll do, let's see, which one? Let's do 29 together. Make sure I've got the right one here, okay. So what I'm gonna do, my first function here is gonna be 16x to the power of 3 plus 16x to the power of 2 equals x plus 1. And then greater than or equal to x plus 1. But my first function and my second function stay the same. So for 29, let's say f of x is 16x to the power of 3 plus 16x to the power of 2. And then my second function, we'll call it g of x, just kind of arbitrarily, is going to be x plus 1. Just making notes to yourself, right? This would be a linear function. There's just one x. This is a cubic, right? X to the power of 3. So let's graph these to see what they look like and then map it back to what we were just talking about. So let's see here. Where's my Desmos? First, I'm going to put in my f of x function. So that's 16x to the power of 3. And then step it down so you're not adding in that power, plus 16x squared. So looking at this function here, okay, this is my cubic. One thing that I want you to start noticing is the highest power of x is 3, right? And so even though there's some stuff going on in the middle here, right? So there is some stuff that's going on here, but the general form, right, is coming up from the bottom here, and then it's taking off like this, right? So some stuff happened in the middle, but if you go back and look at our general form of a cubic, right, or a power function, x to the power of 3, the general form looks like this, coming up from the bottom and then taking off. So when we add in more terms, stuff happens in the middle, but it's important to remember that the general kind of incoming, outgoing shape is going to be the same, and it depends on what the highest power of x is. So that's just good to keep in mind, right? And that's why it's so useful to know what these general shapes are, especially these first 3, right? Because when I saw that x to the power of 3, I thought, oh, okay, I know kind of generally that it's going to look like this, and then some stuff will happen in the middle, right? Because there's more than one term, but then it'll take off, so it'll kind of look like this, right? So that's just kind of a side note, but it's good to know. So here's our first function. Then I'm going to add on my second function, which is just x plus 1, which again behaves just the way I expected it to. X plus 1 is a straight line. So what we have is we have this straight line intersecting the graph 1, 2, 3 times, right? So the solutions here, where these things are equal to each other, these things are equal to each other at x equals -1, negative 0.25 or negative 1 over 4, and then positive 0.25 or 1 over 4. Desmos likes the decimal approximations, and it makes sense. If we're talking about a number line, we're typically talking about decimal approximations. So the solutions here are where these graphs intersect. So f of x equals g of x at the intersections. Which was at, oh shoot, -1, 0, okay, -1, 0, -0.25 and 0.75, and then I want to say 0.25 and 1.25. Let me make sure. Okay, -0.25, 0.75, 0.25, 1.25. Good. So these are the solutions when they're equal to each other, right, where they intersect. If I want to find an inequality, right, where f of x is greater than or equal to x plus 1, or g of x, f of x greater than or equal to g of x. Okay, so now the outputs of f of x, which is the blue line, have to be greater than or equal to the green line. Okay, so if I'm looking here from this point between this solution, oops, hey, there we go. All the way along here, all these outputs are greater than the outputs of the green line, right? Here, my outputs of f of x are less than the outputs of g of x. So that's not included in the solution to the inequality, but here we take off and my solutions are larger than the green line again. And I'm pretty sure, let's just write these down, but from x equals -1 to -0.25, So this is true from -1, 0 to -0.25, 0.75, and past 0.25, 1.25. Okay, so including these points, we have f of x is greater than g of x at x between and equal to -1 to -0.25 and x greater than or equal to 0.25. Oops, need more room. Okay. Which in interval notation, this is going to look like -1 up to -0.25 union, including 0.25 up to infinity, which gets a round bracket because infinity is not a number. Whew. Okay. I'm out of time, but definitely go through and try some of these on your own, right? I think what I wanted to do was I wanted to see if I could do is greater than or equal to x plus 1 just to confirm my answers. But remember, when you give it inequalities, it only shows you the regions where this is true. So there's no curvature anymore, but you can confirm that it goes from -1 up to -0.25 is what it should be. And then from positive 0.25 all the way to infinity, even if you zoom out. Good. Awesome. Any questions? So we'll keep talking about functions and graphs next day, of course, but maybe read ahead in those notes, and what you'll find is that we're doing a lot of the same stuff as in chapter 1, just building on it now. Okay. I'm not seeing any questions, so I'll stop this recording